rules by which the checkers move. The mathematics may be applied in a complex situation to figure out what happens in the next move, what's a good move to make, in a complicated situation, but very little mathematics is needed in the fundamental, simple character of the basic laws. Now, the strange thing about physics is that for the fundamental laws, we still need mathematics. For example, I give two examples, one in which we really do not and one in which we do. There's a law in physics called Faraday's law, which says that in an electrolysis, the amount of material which is deposited is proportional to the current and to the time that the current is acting. And that means that the amount of material is proportional to the charge which goes through the system. Sounds very mathematical. But what's actually happening is that electrons going through the wire each carry one charge. And to take an example, a particular example, it may be that to deposit one atom requires one electron to come. And so the number of atoms that are deposited is necessarily proportional to the number of electrons that flow, and thus to the charge that goes through the wire. So the mathematically appearing law has as its basis nothing very deep, requiring no real knowledge of mathematics, that one electron is needed for each atom in order for it to deposit itself. That's that's mathematics. I had to say number one. But it's not the kind of mathematics I'm talking about tonight. Now, if we take, on the other hand, Newton's law for gravitation, which has these aspects which I wrote down last time just to impress you with the speed at which mathematical symbols can carry information. We said that the force was proportional to the product of the masses of two objects and inversely is the square of the distance between them, and that bodies react to forces by changing their speeds or changing their motions in the direction of the force by amounts proportional to the force and inversely proportional to their masses. Now that's words, all right, and I didn't have to write the equation, but nevertheless it's kind of mathematical, and we would wonder, how can this be a fundamental law? How can this planet out there look, what does it do to it? It looks at the sun and it sees how far away it is, and it decides to calculate on its internal adding machine the inverse of the square of the distance, and that tells it how much to move. This is certainly no explanation of the machinery of gravitation. So you might want to look further, and various people have tried to look further. Newton was originally asked, it doesn't mean anything, it doesn't tell us anything. He says, it tells you how it moves. It should be enough, I told you how it moves, not what. But people are often unsatisfied without a mechanism, and I would like to describe one theory which has been invented among others, of the type that you might want, that this is the result of large numbers. And that's why it's mathematical. And I give this theory, perhaps you've thought of it yourself. Every once in a while some student comes running in, he suddenly explains gravitation. Suppose that in the world, everywhere, there are flying through us at very high speed a lot of particles that come equally in all directions. They're just shooting by, and once in a while hit us in a bombardment. But we and the sun are practically transparent for them, nearly. But some hit, and so it's not completely transparent. Then look what would happen. If the sun is here, and the earth is here, then if the sun weren't here, there would be particles bombarding from all sides, giving little impulses by the rattle of these bang, bang, the few that hit, which would not shake the earth in any particular direction, because there is many coming from one side as the other, from top, from bottom. However, when the sun is here, the particles which are coming in this direction are partly absorbed by the sun because some of them hit the sun and don't go through. Therefore, the number that are coming from this direction toward the earth is less than the number that are coming from the other side, because here they have no opposition from no sun there. And it's easy to see, after some mental effort, that the further the sun is away, the less in proportion of all of the particles are being taken out of the possible directions in which particles can come. I mean, the solar size appears smaller. And, in fact, inversely is the square of the distance. So there will therefore be an impulse toward the sun on the earth that's inversely as the square of the distance, and is the result of large numbers of very simple operations, just hit one after the other from all directions. And therefore the strangeness of the mathematical relation will be very much reduced, because the fundamental operation is much simpler than calculating the inverse of the square of the distance. This machine does the calculating, these particles bouncing. Only trouble with it is that it doesn't work for other reasons. Every theory that you make up has to